Yeah. Okay. So going back to this, let's look at this question over here. So we have P which is pointing to, we said there's only one pointer P. All right. So when you're looking at this particular pointer P, we said we need to figure out, see, remember the Q has two pointers, front and rear. So the question is, where should P point to in order that all operations are ordered? So if P was pointing to the front, then to deletion of an element would be order 1. That is, DQ would be order 1. But on Q would be ordering. Why? Because we don't have W. If it was a doubly linked list, it would have been different. But since I'm having only a singly linked list, singly linked circular list, on Q would have been ordering. On the other hand, if P points to the rear, then the P pointer next should point to the front of the P. Okay. I generally use what is called, I start as always with a dummy node and I point P to the dummy node and I do ensure that the rear is inserted over here and rear pointer next is the front. Okay. So this is precisely what I do. So P points to the rear. Dummy node is not required because if P is equal to null, then that means the list is empty and you need to do a little more work when you're inserting. It's not. Okay. So this is something that you can do because every time you're doing a delete operation. So this is how you use circularly linked list as okay. So on Q, DQ, Q empty. There's nothing like Q full because its lists can keep growing. Linked list as a Q. So if you had a Q full operation that was there, then all that you would do is you will always return back to, you will just say that it's never full. Okay. Now let's go back to the next question. This is what it was. And this is the second question, is the two-stack question. What we're saying is we're talking about the implementation of an ADT two-stack. So what we do is we have, it's a single array, but we have two stacks. And we want to make it as efficient as possible. As we had already told in the class, the stack pointer now points to pointer has two pointers. I mean, remember the stack pointer we said, your stack can grow from the top or from the bottom. It can go from here or it can grow from here. It doesn't matter. It grows in this direction and grows in this direction. So because it implements two stacks, you have two stack pointers and you have two tops.
And we can't see the screen.
Oh, sorry. Thank you. Sorry, I didn't notice this. Yeah.
Yes, no.
Now it's okay. So you have two stacks over here implemented in a single array. That's the important point. And you have one stack which grows in this direction, another stack which goes in this direction. So you need two stack pointers. So you have two tops. So you have a top 1 and top 2. Okay. In the context of the stack, because it's implemented using an array, we do have a stack full operation. And when does this happen? SP1 equals SP2 minus 1 or vice versa, depending upon where you started. So this was a very important operation that we were looking at for in the two stack problem. Okay, all of them are quite simple, not very complicated. Let me go back to the okay, so is this clear? This one is quite clear, right? Oh, I have said SP1 plus 1. Okay.
Ma'am, time complexity.
Time complexity will all be order 1 for each of the operations because one stack is going from this side, another stack is going from this side. Okay, I have, if I look at my class or ADT2 stack, I have an ADT2 stack here. And this guy has pointers, top of stack 1, TOS2, and then I have, yeah, this is what we had, right? And then that's it. So basically 2 different pointers to the top of the stack, and you only need to check whether those position on the stack, for example, SP1, SP2 is, we are always pointing to the top of the stack. So it's all going to be order 1 because all that I'll do is in one case I'll do TOS minus minus and TOS plus plus. That's all. Okay. Oh God, sorry, I forgot to stop share. This should still show my feature. Yeah. So basically you have 2 pointers pointing to the top of the stack, and you increment, one you increment, one you decrement. That's all. So if this is TOS1 and this is TOS2, TOS1 is incremented, TOS2 is decremented. Sorry, TOS1 is decremented and TOS2 is incremented, and you push elements to the stack. And each one of them is working independently. The important point is to use the space efficiently, and that is where, when the 2 of them overflow, that is where we worry about. Okay. Now let's go on to the next question. All right. This is a nice one. Sequence of ones. It's like this. I have, as I say, sequence of ones or sequence of zeros. Ones follow the sequence of ones. Okay. Like this. It's an infinite sequence. Okay. And so what happens is it's like this 0, 0, 0, let's say. And somewhere, 1, 1, 1 starts. Problem is this is an infinite. Oh, sorry. Go back to my iPad. All right. So what we do is the following. Let me get the participant list here. I'm just going to stop the video because I cannot see. Okay. So what we do is, what we are saying is, if I give an index into the element and I ask in this infinite sequence, at index I, what is the element? It will return either 0 or 1. There's some oracle of function that's. So now, how do I find this boundary, which happens somewhere between 0 and 1? That is the question. And we want to do it fast. This is essentially a problem on learning about search and doing complexity. Okay. And learning that because it's an infinite sequence, you will have to do searching fast actually. And if I given the length of the sequence, obviously you will be able to use binary search, right? If the length of the sequence was known. If length is known. And that will give you log n, and that's fantastic. But I do not know the length. Okay, that's the fundamental problem. So when you want to search fast and also realizing that exponential actually grows faster, right? We saw this, the recursive of n minus 1 grows fast. So what was the objective here? We just wanted to find this location. So what we do is we make the index grow exponentially and we call this order. So wherever there is a sign change, I start with some 2 to the power of I. Okay. And then next I look at 2 to the power of I plus 1. If both of them are 0, this also returns 0, I let it be. Then look at is of 2 to the I plus 1 and is of 2 to the I plus 2. First of all, there's no sanctity about 2. You can start with 10 to the power of I. Just that since we deal with bits, I start with 2, it doesn't really matter. If you have given an answer that is 10 to the I and 10 to the I plus 1 and you have not got credit, please ensure that you get your credit back. Okay, you can do anything as long as it's exponential such. So once I find the sign change, 10 of I to 10 of I plus 1, I know this is the region which contains the change in somewhere the boundary is there. I know that this guy was 0 and this guy was 1. Then you can, now you have the indices. Now you have a fixed length array between 2 to the I and 2 to the I plus 1. And you can do binary search. Okay. And find this location where the change occurs. A little bit of modification is required. That's all. Okay, to binary search. So that was the, we haven't got checked papers back. Just the marks. Checked papers, but you've got the comments, right? We have, see what happens is checked papers, annotating the scripts. I have done the annotation of the scripts for the question that I corrected, but TAs don't have this Adobe annotator. Okay, so they have not annotated. So if you need any questions, what we have done is they have given you a set of comments and those comments are sent back to you for every question. So it's like, you do your public exam and then we correct without really marking on the paper. Okay. Then the next one is a similar question. Yes, no, maybe, devise an order in algorithm. This is actually similar to, this is called the Dutch national flag problem. And this was, I think this was designed by Dijkstra, if I remember right, long ago. And what you do is, now you have, I think you have, what did I say? Yes, no, and an unsorted array contains the keys, yes, no, maybe. Rearranges the elements such that no's precedes maybe, which precedes yes. So basically you maintain 2 cursors for yes and no. Okay, so this is S here and this is no here. I hope I've not. So what you do is, as long as you have contiguous nodes, move them here, and contiguous S's, you move from here. So what has to be there? In the middle, you should have maybes. Okay. So what you do is, whatever, so basically you've done this over here, and then move from right until contiguous Y. Then let the 2 pointers be low and high. And starting from index low plus 2, if it is maybe, then increment. If it is no, then swap with low and increment. So basically there's a maybe here, increment. But if it is not, then what do? You swap with low and then increment it. That's exactly what you do. That is what I'm saying is this is very similar. I don't know whether I gave you this, given an array, if you're looking at some number of elements, say I said, suppose an array has 0, 5, 0, 4, 3, 0, 7, 8, something like this. I don't know whether I gave you this question, move all the zeros to the end of the array. I think we asked you to preserve the order. Here it does not talk about preserving the order. So what I will do is, if there's a maybe, I will let it be. If there is a no over here, I'll swap and then I will move this guy, move the pointer. That's exactly what the idea is. Yeah. Oh, sorry, again I have. There isn't, okay. What happened? Sorry, I shared the wrong screen. Share iPhone. All right. So basically what's happening is you have the no's, you have the maybes and the yeses. You start one pointer from left, start one pointer from right. As long as there are contiguous no's and contiguous yeses, you keep them quiet. So this is exactly like this problem. It's just that as if I had a sentinel 111 and then any arbitrary set of numbers on the left side and some, let's say, 5, 4, 3, 7, 9 and zeros on the right hand. Exactly like that. So what would you do? You would look for the ones, if the no's are there, you keep, as long as the no's are not exhausted, you keep incrementing this pointer. Similarly, you have a high pointer, you keep on decrementing this pointer as long as the yeses are there. Then you move this guy. If you see a maybe, you let it be. If you see a high here, then you swap with this. And similarly, you keep doing this on the left-hand side. Swap with this increment, decrement high. Because here there was a maybe, Swap these two guys, then you decrement high here. Similarly, you swap with the maybe that is there, if there is a low over here, and then increment through. And keep repeating this until you have exhausted. The 2 pointers cross. High and low will cross. And you're done. Just like you did this, I think you've done this a number of times. In this array, for example, you would have again done this. Crossing of pointers in quicksort. Number of problems we have done like that. Okay. So this is a simpler problem, but some of you got this, I think, if I remember it. But both are perhaps equally hard when you look at the fact that 3 of them have. So this was the third question. And this is a pangram. Pangram is, this example has been given. Sphinx of black quartz, judge me my wow. The lazy, what is that lazy brown? What is that? The quick brown fox jumped over the lazy dog or something like that. That's a very typical Microsoft word statement. And why is it given? Because it's a pangram. So what do you do here in a pangram? This idea is very simple. What do you want to count? You have a count of 1 to 0 through 25 for the letters of the alphabet. Then what you have to do is, if there is an uppercase letter A, you have to convert to lowercase. Okay. And how can this be done? If normally, for example, you look at or if you have the character A, for example, you look at the integer value of A. If I say index A, index A here, A is equal to, yeah, oh, again, sorry. Thank you. This is too much work. I'm very old, for all of this technology. Yeah, it is very simple for this. So what you have is, you can have, remember that the quick brown fox, right, is this question. All of you might have seen this. Brown fox jumped over the lazy dog. Is this correct, guys? TS? Dog. Right? All of you have seen this somewhere or the other, no?
Yeah.
Okay. So what is the problem with this? I can have, this Q can be a capital letter. This is, and let's say I had B, which was capital, and so on. I need to convert this. So what I have to do is, if there is a capital letter, then I subtract the index of the integer value of capital A. Okay. If it's a small letter, then I subtract the index of integer value of small a. Okay. And then what do? Then once I have subtracted, I increment count, increment the array count. If this number is between 0 and 25. After subtracting, if the value is between 0 and 25, I increment count. Okay, increment the array count. And to find out if you do not know what the ASCII value of small a or capital A is, you find this out by saying caps A equals, find out the int of quoting. Do that. Or whatever. I don't remember exactly what this comment is, but any form if you have written is fine. And this is important. And I can say small a equals again int of small a. So basically what you're going to look for is you subtract from small a if it is below capital A. Okay, because you'll find out whichever number is larger. You'll find that I think I don't remember now. Perhaps capital A is smaller, smaller, or which is 65. 65 is capital A. I'm not sure. Anyway, whichever is smaller, and you look at the new characters. Let's say I take every letter of this alphabet. See whether whichever is larger, for example, or whichever is smaller. See whichever range it is in, and subtract 26. Subtract the index of caps A, or depending upon. So what I do is I find a new letter. I take that new letter that I see, depending upon the range of it, whether it's between these two values. I don't remember which is larger and which is smaller. Then you subtract either small a or you subtract capital A. And then once you subtract it, if it is within the range 0 to 25, you increment the count. As simple as that. And once you have incremented, finally, once the string has been exhausted, I've come to the end of the string. Then what do? I check array count. If all elements are non-zero, then it's a pangram. Okay. Okay, let's just one GK question. Why does this word processor give you this fixed brown fox jumped over the lazy dog? Anyway, think about it. And why is a pangram important for a word processor? If you read Kanut's document, you will know. Okay. Anyway, so this was the pangram. And this, I suppose, was very easy, right? All that you had to do was find out the sum of two numbers is equal to some other number. So you're starting from the left, starting from the right, and we said any one solution. Just check whether the sum of two numbers is equal to x or not. So again, start from the left, start from the right, and whenever the let's say a of I plus some a of j equals x, you stop. It's possible that, and remember this is a sorted array. Because it's a sorted array, it's possible that the sum is not found. And then what will happen? The pointers will cross, or you'll never, the pointers will cross and you'll never have this condition satisfied. So it's quite it's not involved, and then again, you don't need more than we're just looking for one example. The complexity is again order n. Okay. Then coming to the last two problems, both of them are more or less identical. And the idea is just the following. What we're saying is we're starting with a stack or a queue of size 0 initial.
Ma'am, we are seeing the PDF.
Oh, sorry. And okay, so let me repeat this again here. So basically you start with a pointer from this side and this side, and as soon as a of I plus j equal to x, you stop. If the pointers cross without your finding any sum which matches this, so what will happen is you're starting from this side and starting from this side. Since this is a sorted array, the sum can be greater than, or for example, it's possible the first time itself the sum is less than the given x, then you're out. So you just keep on checking until that until you find a particular case where a of I plus. I think the code is given there, right? I think the code has been put in over here in the solutions. I think you can look at it. Okay, so you look at the left and right, and we're looking at from until left less than right, because sum of two numbers, then right minus minus, and so on, because you're looking at sum of two numbers. So the same number given is not okay for us. And then otherwise it's less than, greater than, less than, and you are done with this. It's a very simple piece of code. Okay. Then the last question, which many of you have answered and some have not answered too well. All that we expected was, you don't have to tell me about amortized analysis because we have not taught you amortized analysis. All that we wanted you to, this gives you a precursor to understand this, that the important point is initially the stack or queue size is 0. Then once you insert an element, it becomes 1, then it becomes 3, then it becomes 7, then it becomes 15, and so on, if I'm only pushing elements. Remember that anything pushing is the worst case and popping is the worst case when you have to keep on increasing or decreasing the size of the array. So when I increase the next element, for example, then immediately what happens? I need to increase the size, therefore I have to copy this one element. Then I can insert 2 more elements before I need to increase the size. Okay. So when it's 3 elements, I need to add 3, 7, 15, and so on. And when you sum this, you will find that the number of steps in which you need to actually do the sum is only log n. And when you do the sum using geometric series, and because this copying happens so many times, anyway, there is the order one. See, remember to insert n elements into a stack or a queue. Queue is anyway order n. Okay, some constant times some fn. Then all that you're going to do is you're going to do some extra this many operations, and this will also turn out to be order of fn. It's c times fn. I think c is 2 if I remember right. That's all that you require. So we didn't want you to talk about amortization and other things. We were just looking for this counting over here. We just wanted you to count. And the point is, it does not matter whether you, whether you are, see, the same thing for pop too, right? Suppose I do push and pop. It's never going to be a bang bang. Why so? Because we are saying only when it becomes full, you're doubling it. And when it becomes quarter the size, you are halving it. So it's never going to be that, you push, you copy, then pop, you copy. That's not going to happen. So what is going to happen? The worst case will be a whole lot of pushes and a whole lot of pops. Okay. And in between, for example, you'll never require this much of incrementation. This is the argument that we was looking for in the solution to this problem. Okay, stop here. And I have recorded this. I'll put it up on the web. And anyway, enjoy your holiday. I have been told just one question. There is a comment from the dean that we will have a lab assignment next week. Okay, this week we are not giving you anything. And Dean has said not to give anything next week also. I want to know your feedback on that. Because he said no assignment deadlines, no deadlines as soon as they come back, no assignments which require the entire weekend and so on. So Vineet and Shanti, can you give me some feedback on this? We will have one trees assignment. Do you want to have the test? No, he said no test particularly. We can not as soon as you come back, but we can do the test, one test on Friday or the following week. And next week we'll have a regular assignment. Sentence has all letters of the alphabet. Yeah, that's right.